Hello, this is Dr. Morris. I'm starting lecture number 2, which has to deal with chemical and molecular anatomy. This is a part of a continuing lecture series for Anatomy and Physiology 1. Again, my name is Dr. Steve Morris, and we will go ahead and proceed with the lecture. Molecular level anatomy has to deal with the chemical level of organization in the human body. Our study of the human body begins at the chemical level of organization. Chemistry is basically the science that deals with the structures of matter, defined as anything that takes up space and has mass. The smallest stable unit when we talk about and deal with the human body, the smallest stable unit of matter is called the atom. The unique characteristics of each of these objects, living or non-living, results from types of atoms that are involved in the ways that those atoms combine and interact. It's important to become familiar with the chemical principles governing those interactions in order to understand the anatomy and the physiology of cells, tissues, organs, organ systems, and the human body. The next area we're going to talk about are subatomic particles. Atoms are composed of subatomic particles. Although many different subatomic particles exist, only 3 are important in understanding the chemical properties of matter, and these are protons, neutrons, and electrons. Protons and neutrons are similar in size and in mass, but protons, which have the designation of 1p, which is a positive charge, have a positive electrical charge, whereas neutrons are electrically neutral and basically are uncharged. When we talk about electrons, they're much lighter than protons, and then they're only about 1 in 186,000th as a bare negative electrical charge. The mass of an atom is therefore determined primarily by the number of protons and neutrons in the nucleus. The mass of a large object, such as your body, is the sum of the masses of all the components of the atoms. The atomic structure. Atoms normally contain equal numbers of protons and electrons. The number of protons in an atom is known as the atomic number. Hydrogen, designated by the capital letter H, is the simplest atom and an atomic number of 1. Hydrogen atoms is an atom of hydrogen. It contains 1 proton. It contains 1 electron as well. The proton is located in the center of the atom and forms the nucleus. Hydrogen atoms seldom contain neutrons, but when neutrons are present, they are also located in the nucleus. All atoms other than hydrogen have neutrons as well as protons in their nuclei. Another concept that I'd like you to appreciate is called the electron cloud. The electron orbits the nucleus at high speeds, forming a spherical electron cloud. In a two-dimensional representation, the electron occupies a circular electron shell. The electron shell, and again in a two-dimensional representation, the electrons occupy a circular electron shell. One reason an electron tends to remain in its electron shell is that its negatively charged electron is attracted to the positively charged proton. The attraction between the two opposite electrical charges is an example of an electrical force. Electrical forces are involved in many of the physiological processes that we will be dealing with in human anatomy. In a two-dimensional model depicting the electron in an electron shell around the nucleus lets us visualize the components of the atom. A typical hydrogen nucleus contains a proton and no neutrons. A deuterium nucleus contains a proton and a neutron. A tritium nucleus contains a pair of neutrons in addition to a proton. Here's an illustration that gives you the example of the various types of hydrogen atoms and how they can exist. Again, we talked about the hydrogen 1 with the electron, the proton center. Again, the orbit, the electron shell, noted by the attraction between the negatively charged electron and the positively charged proton. Here you can see hydrogen 2, the deuterium, and then the hydrogen 3, the tritium representation. Again, looking at the electrical charges of the electron being negative, proton being positive in this representation. The dimensions of the electron cloud determine the overall size of the atom. To get an idea of the scale involved, consider that if the nucleus were the size of a tennis ball, the electron cloud would have a radius of about 10 kilometers, roughly 6 miles. Atomic measurements, in reality, we look at atoms are so small that the atomic measurements are most conveniently reported in a measurement of unit referred to as a nanometer. 1 nanometer is a meter. The very largest atom approaches approximately 0.5 nanometers in diameter. Atoms can be classified on the basis of their atomic number into groups called elements. Each element includes all the atoms that have the same number of protons and thus the same atomic number. Only 92 elements exist in nature, although about 24 additional elements have been created through nuclear reactions in research laboratories. Every element has a chemical symbol and abbreviation recognized internationally. Atomic nuclei are unaltered by ordinarily chemical processes. Elements cannot be changed or broken down into simpler substances in chemical reactions. Thus, an atom of carbon always remains an atom of carbon, regardless of the chemical event in which it may take part. There are about 13 principal elements in the human body. The human body also contains atoms of another 13 elements called trace elements that are present in very small amounts. Some of the principal elements are outlined on this slide: oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, potassium, sodium, chloride, magnesium, sulfur, iron, and iodine. We will talk about all of these principal elements in the human body later on in the lecture series. However, principal elements that we are familiar with will be discussed more in detail later on in this particular lecture. Some of the trace elements that we should become familiar with are silicon, fluorine, copper, manganese, zinc, selenium, cobalt, monodubium, cadmium, chromium, aluminum, and boron. I skipped one. The atoms of a single element can differ in terms of the number of neutrons in the nucleus. For example, although most hydrogen nuclei consist of a single proton, approximately 0.015%, also contain 1 neutron, and a very small percentage contains 2 neutrons. Atoms whose nuclei contain the same number of protons but different numbers of neutrons are called isotopes. Different isotopes of an element have essentially identical chemical properties and so are indistinguishable except on the basis of mass. The mass number, the total number of protons plus neutrons in the nucleus, is used to designate a particular isotope. The 3 isotopes of hydrogen, which we have looked at earlier, hydrogen 1, or 1 proton and 1 electron, hydrogen 2, or also known as deuterium, which has 1 proton and 1 electron and 1 neutron. Hydrogen 3, also known as tritium, has 1 proton, 1 electron, and 2 neutrons. Again, the illustration that we looked at earlier, typifying hydrogen 1, hydrogen 2, hydrogen 3, and the molecular structure that identifies each of them. The nuclei of some isotopes spontaneously emit subatomic particles or radiations in measurable amounts. Such isotopes are also called radioisotopes, and the emission process is called radioactive decay. Again, later on in the lecture series, we will discuss isotopes and radioisotopes in more detail. Strongly radioactive isotopes are dangerous because the emission can break down molecules or break molecules apart, destroy cells, and otherwise damage living tissue. Weakly radioactive isotopes are sometimes used in diagnostic procedures to monitor the structural and functional characteristics of internal organs. Decay rate or half-life is another term that you should become familiar with. Radioactive isotopes differ in how rapidly they decay. The decay rate of a radioisotope is commonly expressed in terms of half-life, the term required for half of a given amount of isotope to decay. The half-lives of radioisotopes range from fractions of a second to billions of years. Another term that you should become familiar with is the atomic weights. A typical atom of oxygen, for example, which is an atomic number of 8, contains 8 protons but also contains 8 neutrons. The mass number of this isotope is therefore 16. The mass number of other isotopes of oxygen depend on the number of neutrons present. Mass numbers are useful because they tell us the number of subatomic particles in the nuclei of different atoms. The atomic weight, the mass number, do not tell us the actual mass of the atoms. For example, they do not take into account the masses of the electrons or the slight differences between the mass of the electron and that of the neutron. The actual mass of the atom is known as the atomic weight. A Dalton, the unit used to express the atomic weight is the Dalton, also known as the atomic mass unit, also referred to as AMU. 1 Dalton is very close to the weight of a single proton. Thus, the atomic weight of most common isotope of hydrogen is very close to 1, and that the most common isotope of oxygen is very close to 16. Atoms participate in chemical reactions in a fixed numerical ratio. To form water, for example, exactly 2 atoms of hydrogen combine with each atom of oxygen. But individual atoms are far too small and too numerous to be counted. To overcome this difficulty, chemists use a unit referred to as a mole. Avogadro's number. For any element, a mole is a quantity with a weight in grams equal to that element's atomic weight. The reason that a mole is so useful is that 1 mole of a given element always contains the same number of atoms as 1 mole of any other element. That number, Avogadro's number, is about 600 billion trillion. Expressing relationships in moles rather than in grams makes it much easier to keep track of the relative number of atoms in chemical samples and processes. Electrons and energy levels is another concept which you will need to appreciate as well. Atoms are electrically neutral. Every positively charged proton is balanced by a negatively charged electron. Thus, each increase in the atomic number is accompanied by a comparable increase in the number of electrons orbiting the nucleus. Within the electron cloud, electrons occupy an orderly series of energy levels. Electron orbits. Although electrons in an energy level may travel in a complex orbit around the nuclei, for our purposes, the orbits can be diagrammed as a series of concentric electron shells. This was shown to you previously in another illustration. The first electron shell, the one closest to the nucleus, corresponds to the lowest energy level. Each energy level is limited in the number of electrons it can hold. The first energy level can hold at most 2 electrons, while the next 2 levels can each hold up to 8 electrons. The electron in an atom occupies successive shells in an orderly manner. The first energy level is filled before any electron can enter the second, and the second energy level is filled before any electrons can enter the third. The outermost energy level forms the surface of the atom. The number of electrons in this level determine the chemical properties of the element. Atoms with unfilled energy levels are unstable. That is, they will react with other atoms, usually in the ways to give them full outer electron shells. In contrast, atoms with a filled outermost energy level are stable and therefore do not readily react with other atoms. Here is another illustration indicating to you the various energy levels that I've discussed earlier. This being the first energy level, as you follow the arrow, demonstrating the electron orbit. This representing a second electron level as you look at the first energy level and then the second energy level. A typical hydrogen atom has one proton and one electron. The electron orbiting the nucleus occupies the first energy level, diagrammed by the electron shell. An atom of helium has two protons, two neutrons, and two electrons. The two electrons orbit in the same energy level. The first energy level that holds only two electrons. Now, in a lithium atom with three protons, four neutrons, and three electrons, and a third electron occupies the second energy level. The second energy level can hold up to 8 electrons. A neon atom has 10 protons, 10 neutrons, and 10 electrons. Thus, both of the first and the second energy level are filled. A hydrogen atom has one electron in the first energy level, and the level is thus unfilled. A hydrogen atom readily reacts with other hydrogen atoms or with atoms of other elements. A helium atom has 2 electrons in the first energy level. Because its outermost energy level is filled, a helium atom is very stable. It will not ordinarily react with other atoms. A lithium atom has 3 electrons. Its first energy level can hold only 2 of them, so a lithium has a single electron in the second unfilled energy level. As you would expect, lithium is extremely reactive. A second energy level is filled with a neon atom with an atomic number of 10. Neon atoms, like helium atoms, are thus very stable. The atoms that are most important to biological systems are unstable because those are the atoms that interact to form larger structures. That's an important concept to recognize in biological systems and in the human body. Chemical bonding. Elements that do not readily participate in chemical processes are said to be inert. Helium, neon, and argon have filled outermost energy levels. These elements are called inert gases because their atoms neither react with one another nor combine with atoms of other elements. Elements with unfilled outermost energy levels, such as hydrogen and lithium, are called reactive because they readily interact or combine with other atoms. In doing so, these atoms achieve stability by gaining, losing, or sharing electrons to fill their outermost energy level. The interactions often involve the formation of chemical bonds which hold the participating atom together once the reaction is ended. There are 3 basic types of chemical bonds. These are important for you to know: ionic bonds, covalent bonds, and hydrogen bonds. When chemical bonding occurs, the result is the creation of new chemical entities that we call molecules and compounds. The term molecule refers to any chemical structure consisting of atoms held together by covalent bonds. A compound is any chemical substance made up of atoms of 2 or more elements, regardless of the type of bonding joined. Not all molecules are compounds, because some molecules consist of atoms and only one element. The example, 2 oxygen atoms can be joined by a covalent bond to form a molecule of oxygen. And not all compounds consist of molecules because some compounds, such as ordinary salt, sodium chloride, are held together by ionic rather than covalent bonds. Many substances, however, belong to both categories. Water is a compound because it contains 2 different elements, hydrogen and oxygen, and it consists of molecules because the hydrogen and the oxygen atoms are held together by covalent bonds. As we shall see in subsequent sections, most biologically important compounds from water to DNA are molecular. The human body. The human body consists of countless molecules and compounds, so it is a challenge to describe these substances and their varied interactions. The ionic bonds. As the name implies, ionic bonds form between ions. Ions are atoms or molecules that carry an electrical charge, either positive or negative. Ions with a positive charge are called cations. Ions with a negative charge are called anions. Ionic bonds are chemical bonds created by electrical attraction between anions and cations. Ions have an unequal number of protons and electrons. Atoms become ions by losing or gaining electrons. If we assign a value to the charge on a proton, the charge on an electron is the number of protons is equal to the number of electrons. An atom is electrically neutral. In the formation of an ionic bond, we see one atom, the electron donor, loses one or more electrons and becomes a cation and a positive charge. Another atom, the electron acceptor, gains those same electrons and becomes an anion with a negative charge. Attraction between the opposite charges then draws the two ions together. Here's another illustration demonstrating to you various types of molecular compounds that we have described earlier. The sodium chloride, or the salt, again demonstrates the formation of a specific ionic compound. In the first step, we see formation of ions. You see the sodium atom and the chlorine atom. In step 2, you see the attraction between the opposite charges, the positive charge as we see from the sodium ion and the negative charge from the chlorine ion. Then in the third step, we see the formation of the ionic compound, a sharing in the outermost energy level of these common charges between sodium and chloride, forming sodium chloride, commonly referred to as salt. Ionic bonding in table salt goes through those 3 steps as I mentioned earlier. Step 1, sodium atom loses an electron, which is accepted by chlorine. Step 2, because sodium and chloride ions have opposite charges, they are attracted to one another. And then in step 3, the association of sodium and chloride ions to form the ionic compound. The combination of oppositely charged ions forms an ionic compound, in this case sodium chloride, otherwise known as table salt. The large number of sodium and chloride atoms interact to form a highly structured crystal, held together only by the electrical attraction of oppositely charged ions. Although sodium chloride and other ionic compounds are commonly in body fluids, they are not present in intact crystals. When placed in water, ionic compounds dissolve and the component ions and cations will separate. Covalent bonds. Some atoms can complete their outer electron shells not by gaining or losing electrons, but by sharing electrons of other atoms. Such sharing creates covalent bonds between atoms involved. This, again, is an illustration demonstrating to you an electron shell model and structural formulas. This shows the hydrogen, oxygen, carbon dioxide, and nitric oxide. These are common molecular compounds. Again, we will allude to these later on into the lecture. In covalent bonds, in a hydrogen molecule, 2 hydrogen atoms share electrons such that the atom has a filled outermost shell. The sharing creates a single covalent bond. Molecular hydrogen consists of a pair of hydrogen atoms. In a chemical shorthand, molecular hydrogen is indicated where a capital H is the chemical symbol for hydrogen, and the subscript 2 indicates the number of atoms. Molecular hydrogen is a gas that is present in the atmosphere in very small quantities. The two hydrogen atoms share the electrons, and each electron whirls around both nuclei. The sharing of one pair of electrons creates a single covalent bond. Again, the illustration illustrating what we just discussed about the hydrogen atom and the sharing of electrons in the outermost shell. In an oxygen molecule, two oxygen atoms share two pairs of electrons. The result is a double covalent bond. Oxygen, with an atomic number of 8, has 2 electrons in its first energy level and 6 in its second. The oxygen atom attains a stable electron configuration by sharing 2 pairs of electrons, thereby forming a double covalent bond. In a structural formula, a double covalent bond is represented by 2 lines. Molecular oxygen is an atmospheric gas. That is very important to most organisms. Our cells would die without relatively constant supply of oxygen. In our bodies, chemical processes that consume oxygen generally also produce carbon dioxide as a waste product. The oxygen atom in a carbon dioxide molecule form a double covalent bond with carbon atom. Again, the illustration that you've seen earlier, now we'll focus upon the appearance of the oxygen in the bond noted in section B. Again, you see the sharing of the electrons forming the double covalent bond. Also, the bond is described in carbon dioxide, the waste product by most biological cells, and especially as we talk about the human body. Again, we see the bonding that occurs, double covalent bonding between the carbon and the oxygen molecule as well. In carbon dioxide molecule, a central carbon atom forms a double covalent bond with 2 oxygen atoms. In nitric oxide molecule, it's held together by a double covalent bond, but the outer electron shell of nitrogen atoms requires an additional electron to be complete. Thus, nitric oxide is a free radical which reacts readily with another atom and molecule. Covalent bonds usually form molecules that complete the outer energy level of the atoms involved. An ion or molecule that contains unpaired electrons in its outermost energy level is called a free radical. Free radicals are highly reactive. Almost as fast as it forms, a free radical enters an additional reaction that are typically destructive. For example, free radicals can damage or destroy vital compounds such as proteins. Free radicals sometimes form in the course of normal metabolism, but cells have several methods of removing and interacting with them. It has been suggested that the cumulative damage produced by free radicals inside and outside our cells is a major factor in the aging process. Nitric oxide, represented by capital N, capital O, is a free radical that has important functions in the body. It is involved in a chemical communication in the nervous system, in the control of blood vessels diameter, blood clotting, and in defense against bacteria and other pathogens. Non-polar covalent bonds. Covalent bonds are very strong because they share electrons and hold atoms together. A typical covalent bond, the atoms remain electrically neutral because each shared electron spends just as much time at home as away. Many covalent bonds involve many covalent bonds involve an equal sharing of electrons. Such bonds, which occur, for instance, between 2 atoms of the same type, are called nonpolar covalent bonds. Nonpolar covalent bonds, especially those between carbon atoms, create a stable framework of large molecules that make up most of the structural components of the human body. Nonpolar covalent bonds are an important concept for you to recognize. Polar covalent bonds involving different types of atoms, may instead involve unequal sharing of electrons because the elements differ in how strongly they attract the electron. An unequal sharing of electrons creates a polar covalent bond. Example, in a molecule of water, an oxygen atom forms a covalent bond with two hydrogen atoms. The oxygen nucleus has a stronger attraction for the shared electron than for the hydrogen atom. As a result, the electron spends more time orbiting the oxygen nucleus than orbiting the hydrogen nucleus. The unequal sharing of electrons makes polar covalent bonds somewhat weaker than non-polar covalent bonds. Polar covalent bonds often create polar molecules that have positive and negative ends. Polar molecules have very interesting properties. We will consider the characteristics of the most important polar molecules in the body, water. In a later section, we will go into a lot more detail. Here is another illustration. Again, all of these illustrations are out of your textbook, but again shows bonding between the hydrogen atoms, two hydrogen atoms sharing the unfilled outermost shell with the oxygen atom. Again, charges on the water molecule, as we can see. The formation of the water molecule, thusly, we see the hydrogen ions, both of which are sharing electrons in the outermost space. Since the charge is greater around the oxygen atom, then most of these electrons spend most of their time circulating around the oxygen atom versus the shell that surrounds the individual hydrogen atoms. Polar covalent bonds and the structure of water. In forming a water molecule, an oxygen atom completes its outermost energy level by sharing electrons with a pair of hydrogen atoms. You saw this in the previous illustration. The sharing of these hydrogen atoms are the electrons from the hydrogen atoms and the outermost shell of the oxygen atom. The sharing is basically unequal because the oxygen atom holds the electron more tightly than do the hydrogen atoms. Because the oxygen atom has two extra electrons much of the time, it develops a slight negative charge, and the hydrogen atom becomes weakly positive. The bonds in a water molecule are polar covalent bonds. As you can see again on this illustration, as the hydrogen ions now become weakly positive, and we see that the oxygen atom becomes negative. Hydrogen bonds. Covalent and ionic bonds tie atoms together and form molecules and compounds. There are also comparatively weak forces that act between adjacent molecules and even between atoms within a large molecule. The most important of these weak attractive forces is the hydrogen bond. The hydrogen bond is the attraction between the hydrogen atom of a polar covalent bond and an oxygen and a nitrogen atom of another polar covalent bond. The polar covalent bonds containing the oxygen or the nitrogen atom can be in a different molecule from or in the same molecule as the hydrogen atom. Here's an illustration depicting to you the hydrogen bond. The hydrogen bond too weak to create molecules, but they can change the molecular shape or pull molecules together. The example given is hydrogen bonding occurs between water molecules. At the water surface, the attraction between molecules slows the rate of evaporation and creates a phenomenon known as surface tension. Surface tension acts as a barrier that keeps small objects from entering the water. The example given depicts an insect and its ability to walk on the surface of a pond or a puddle. Surface tension and a layer of tears keep small objects such as dust particles from touching the surface of the eye. Again, the small, weak attraction between the hydrogen atoms, depicted by the red dotted lines. At a cellular level, hydrogen bonds affect the shape, the properties of complex molecules, such as proteins, nucleic acids, including DNA, and they also determine the three-dimensional relationships between molecules. States of matter. Matter in our environment exists in one of three states: solid, liquid, gaseous. Solid maintains their own volume and shape, ordinarily temperatures and pressures. A lump of granite, a brick, a textbook, all are solid objects. Liquids have a constant volume but no fixed shape. The shape of a liquid is determined by the shape of the container. Water, coffee, soda are all examples of liquids. A gas has neither a constant volume nor does it have a fixed shape. Gases can be compressed or expanded. They can fill a container of any shape. The air of our atmosphere is a gas with which we are most familiar with. Whether a particular substance exists as a solid, liquid, or gas depends on the degree of interaction among the atoms in the molecules. Hydrogen molecules have little attraction for one another. In our environment, molecules of hydrogen exist as a gas. Water is the only substance that occurs in all three states: as a solid, for example, ice; as a liquid, water itself; or as a gas, water vapor. And the temperatures, and at temperatures, these have to be compatible with life. Water exists in a liquid state over a broad range of temperatures, primarily because of the hydrogen bonding among the water molecules. The molecular weight of a molecule is the sum of the atomic weights of the component atoms. It follows from the definition of a mole given previously that the molecular weight of a molecule in grams is equal to the weight of 1 mole of the molecules. Molecular weights are important because you cannot handle individual molecules, nor could you easily count the billions of molecules involved in chemical reactions in the body. Using molecular weight, you can calculate the quantities of reactants needed to perform a specific reaction and to determine the amount of product generated. Chemical reactions. Cells remain alive and functional by controlling chemical reactions. In a chemical reaction, new chemical bonds form between atoms, or existing bonds between atoms are broken. These changes occur as atoms in reacting substances or reactants are rearranged to form different substances or products. Metabolism. Growth, maintenance and repair, secretion and contraction all involve complex chemical reactions. Cells use chemical reactions to provide the energy needed to maintain homeostasis and to perform essential functions. All of the reactions underway in the cells and the tissues of the body at any given moment constitute its metabolism. Some basic energy concepts. An understanding of some of the basic relationships between matter and energy is essential in any discussion of chemical reactions. Work is the movement or a change in the physical structure of matter. Energy is the capacity to perform work. Movement or physical change cannot occur unless energy is provided. There are two major types of energy: kinetic energy and potential energy. Kinetic energy is the energy of motion energy that is doing work. When you fall off a ladder, it is kinetic energy that does the damage. Potential energy is stored energy, energy that has the potential to do work. It may derive from object's position, for example, a book sitting on a high shelf, or you standing on a ladder, or from its physical or chemical structure, example, a stretched spring or a charged battery. Kinetic energy must be used in lifting the book to the shelf, in climbing the ladder, in stretching the spring, or in charging the battery. The resulting potential energy is converted back into kinetic energy when the book falls, or you fall, or the spring recoils, or the battery discharges. The kinetic energy can then be used to perform work. For example, the chemical potential energy stored in gasoline is converted to kinetic energy in the engine of your car. The gas is ignited in cylinders driving the pistons up and down and thus ultimately providing kinetic energy to the wheels. Conversion between potential and kinetic energy. Energy cannot be lost. It can only be converted from one form to another. A conversion between potential energy and kinetic energy is never 100% efficient. Each time an energy exchange occurs, some of the energy is released in the form of heat. Heat is an increase in random molecular motion. The temperature of an object is proportional to the average kinetic energy of its molecules. When energy is converted to heat, some usable energy is always lost because heat can never be completely converted to work or any other form of energy. Moreover, cells have no effective way of using heat to perform work. Cells perform work as they synthesize complex molecules and move materials into and out of and within the cell. Some cells are specialized for motion or contraction, for example, a skeletal muscle. Work generates heat. Skeletal muscles at rest contain potential energy in the form of the position of protein filaments and the covalent bonds between the molecules inside the cell. When a muscle contracts, it performs work. Potential energy is converted into kinetic energy, and heat is released. The amount of heat is proportional to the amount of work that is done. As a result, when you exercise, your body temperature rises. There are three types of chemical reactions that are important in the study of physiology. First, decompensation reactions. Second, synthesis reactions. And the third, exchange reactions. Decompensation is a reaction that breaks down molecules into smaller fragments. Decompensation reactions occur outside the cells as well as inside the cells. Example, a typical meal contains molecules of fat, sugar, and proteins that are too large and too complex to be absorbed and used by the body. Decompensation reactions in the digestive tract break these molecules down into smaller fragments before absorption begins. Decompensation reactions involving water are important in the breakdown of complex molecules of the body. In hydrolysis, one of the bonds in a complex molecule is broken, and the components, the water molecule, the hydrogen, and the hydroxyl group, which we'll go into a little bit later, are added to the resulting fragments. In catabolism, collectively, decompensation reactions of complex molecules within the body cells and the tissues are referred to as catabolism. Synthesis is the opposite of decomposition. A synthesis reaction assembles larger molecules from smaller components. Synthesis reactions may involve individual atoms or combinations of molecules to form even larger products. The formation of water from hydrogen and oxygen molecules is a synthesis reaction. Dehydration synthesis. Synthesis always involves the formation of new chemical bonds, whether the reactants are atoms or molecules. Dehydration synthesis, or condensation, is the formation of a complex molecule by the removal of water. Anabolism. Dehydration synthesis is therefore the opposite of hydrolysis. Collectively, the synthesis of new compounds within the body cells and tissues is known as anabolism. Because it takes energy to create a chemical bond, anabolism is usually an uphill process. Cells must balance their energy budget, with catabolism providing the energy to support anabolism as well as other vital functions. An exchange reaction. In an exchange reaction, part of the reactant molecules are shuffled around. Although the reactants and the products contain the same components, for example, A, B, C, and D, those components are present in different combinations. In an exchange reaction, the reactant molecules AB and CD must break apart, which would be referred to as a decompensation reaction, before they can interact with each other to form new compounds such as AD and CB, which would be a synthesis reaction. Reversible reactions. Chemical reactions are, at least theoretically, reversible. Many important biological reactions are freely reversible. Two reactions are occurring simultaneously, one a synthesis reaction and the other a decompensation reaction. At equilibrium, the rates at which the two equations proceed are in balance. As fast as one molecule A, B forms, another will degrade, forming an A plus B. Disturbances in the equilibrium. The result of a disturbance in the equilibrium can be predicted. The rate at which the synthesis reaction proceeds is directly proportional to the frequency of the encounter between A and B. An important concept to learn here early on. Later on in the lecture, we'll talk about enzymes and we'll understand why the importance of these particular direct proportions of the components, such as A and B, are so important. But for now, recognize the rate at which a synthesis reaction proceeds is directly proportional to the frequency of the encounters between A and B. The frequency of the encounters depends on the degree of crowding. The addition of more AB molecules will increase the rate of conversion from AB to A and B. The amounts of A and B will then increase, leading to an increase in the rate of the reverse reaction, or the formation of AB from A and B. Eventually, an equilibrium will be established. Enzymes, energy, and chemical reactions. Most chemical reactions do not occur spontaneously, or they occur so slowly that they would be of little value to cells. Before a reaction can proceed, enough energy must be provided to activate reactants. The amount of energy required to start a reaction is called activation energy. Factors that influence reactions. Although many reactions can be activated by changes in temperatures or acidity, such as changes are deadly to the cells. For example, every day your cell breaks down a complex sugar as a part of your normal metabolism, yet to break down a complex sugar in the laboratory, you must boil it in an acidic solution. Your cells don't have that option. Temperature that high and solutions that are corrosive would immediately destroy living tissue. Instead, your cells, our cells, use a special protein referred to as enzymes. To perform most of the complex synthesis and decompensation reactions in our body, we require these enzymes to facilitate these reactions. Enzymes and activation energy. Enzymes lower the activation energy requirements so a reaction can occur readily in order from 1 to 4 under conditions in the body. These are the 1 through 4 steps that are required for the reaction to take place. This illustration demonstrates the progression of the reaction and the amount of energy that's required for these reactions to take place. Major players include the reactants. A reaction would take place without an enzyme would require, as you can see, a significant amount of energy. Not only is this costly to the system as far as energy reserves, but also has a tendency to slow the reactions. On the other hand, if you see the use of an enzyme involved in a reaction, then you can see the amount of energy that's required would be significantly less, thus also quickening the process of the reaction. Enzymes promote chemical reactions by lowering the activation energy requirement, a key point to know. In doing so, they make it possible for chemical reactions such as breakdown of sugars to proceed under conditions that are compatible with life. Enzymes belong to a class of substances referred to as a catalyst, compound that accelerates chemical reactions without themselves being permanently changed or consumed. An important concept to recognize: enzymes, though they are involved in these reactions, themselves are not permanently changed or consumed by those reactions. A cell makes an enzyme molecule promote a specific reaction. The presence of the appropriate enzyme can accelerate a reaction. An enzyme affects only the rate of the reaction, not the direction of the reaction are the products that will be formed. An enzyme cannot bring about a reaction that would otherwise be impossible. Enzymatic reactions are generally reversible and proceed until an equilibrium becomes established. A complex reaction that supports life proceeds in a series of interlocking steps, and each step is controlled by a specific enzyme. Such a reaction sequence is called a pathway. Synthetic pathways. The steps in a synthetic pathway differ from those of a decompensation pathway. Separate enzymes are often involved. It takes activation energy to start a chemical reaction, but once it has begun, the reaction has a whole absorb or release energy, generally in the form of heat, as it proceeds to completion. If the amount of energy released is greater than the activation energy needed to start the process, there will be a net release of energy. Exergonic and endergonic reactions. Reactions that release energy are said to be exergonic, and more energy is required to begin the reaction than is released. As it proceeds, the reaction as a whole will absorb energy. Such reactions are referred to as endergonic reactions. Exergonic reactions are relatively common in the body. They are responsible for generating heat and maintaining body temperature. Nutrients and metabolites. Nutrients are essential elements of molecules normally obtained from the diet. Metabolites include all those molecules synthesized or broken down by chemical reactants inside our body. Nutrients and metabolites can be broadly categorized as inorganic or organic. Organic and inorganic compounds. Inorganic compounds generally do not contain carbon and hydrogen atoms as their primary structural ingredient, whereas carbon and hydrogen always form the basis of organic compounds. Now, there are important inorganic compounds in the body, and you should be familiar with these. Carbon dioxide, the byproduct of cell metabolism, also considered a waste product. Oxygen, an atmospheric gas that's required in important metabolic reactions in the body. Water, which accounts for most of our body weight. Then inorganic acids, bases, salts, compounds held together partially or completely by ionic bonds. Water and its properties. Water is the single most important constituent of the body, accounting for up to 2/3 of the total body weight. A change in the body's water content can have a fatal consequence because virtually all physiological systems will be affected. Although water is familiar to everyone, it has some highly unusual properties. These properties are a direct result of hydrogen bonding that occurs between adjacent water molecules. Some key properties of water: solubility, reactivity, high heat capacity, and lubrication. Insolubility is a remarkable number of inorganic and organic molecules will dissolve or break up in water, creating a solution. Every solution is a uniform mixture of two or more substances, whether in solid, liquid, or gaseous form. The medium in which other atoms, ions, or molecules are dispersed is called a solvent. The dispersed substances are the solutes. In an aqueous solution, water is a solvent. The solvent properties of water are so important in the human body. Reactivity. In our body, chemical reactions occur in water. Water molecules are also participants in some reactions. Hydrolysis and dehydration synthesis are two examples which were previously discussed. High heat capacity. Heat capacity is the ability to absorb and retain heat. Water has an unusually high heat capacity because water molecules in the liquid state are attached to one another through hydrogen bonding. An unusually large amount of heat energy is required to change the temperature of 1 gram of water. Once a quantity of water has reached a particular temperature, it will change the temperature only slowly. This property is called thermal inertia. Because water accounts for up to 2/3 of the weight of the human body, thermal inertia helps stabilize the body's temperature. Similarly, water's high heat capacity allows blood plasma to transport and redistribute large amounts of heat as it circulates within the body. Water is an effective lubricant. There is little friction between water molecules. Thus, if two opposing surfaces are separated by even a thin layer of water, friction between those surfaces will be greatly reduced. We will see the physiological benefit of this frictionless surface that can be created by water when we talk about specific organ systems: the peritoneal cavity of the abdominal wall, the pleural cavity of the lungs, the pleural cavity of the heart as well. All are based upon two opposing surfaces with a thin layer of water which will reduce friction. Again, these will be discussed in much more detail as we go through those specific organ systems later on in the lecture series. Aqueous solutions. Its chemical structure makes water an unusually effective solvent. The bonds in a water molecule are oriented such that hydrogen atoms are relatively close together. As a result, water molecules have positive and negative poles. A water molecule is therefore called a polar molecule or a dipole. Many inorganic compounds are held together particularly or completely by ionic bonds. In water, these compounds undergo ionization or dissociation. The hydration sphere. In this process, ionic bonds are broken as individual ions interact with the positive or the negative ends of polar water molecules. The result is a mixture of cations and anions surrounding by a water molecule. The water molecules surround each ion, forming a hydration sphere. This is an illustration demonstrating to you an ion in an aqueous solution. As you can see, the charges related to the hydration sphere, hydrogen again having a weak charge against particular molecules. This is an illustration demonstrating to you glucose, another major component in the human system, also in an aqueous solution. In water molecules, oxygen forms polar covalent bonds with two hydrogen atoms. Because both hydrogen atoms are at one end, the molecule has an uneven distribution of charges, creating a positive and a negative poles. Ionic compounds such as sodium chloride dissociates in water as polar water molecules break the ionic bonds. Each ion in solution is surrounded by water molecules, creating a hydration sphere. Hydration spheres also form around an organic molecule containing polar covalent bonds. If the molecule is small, as is glucose, it will be carried into a solution. An aqueous solution containing anions, cations will conduct an electrical current. Cations move toward the negative side or the negative terminal, and the anions move toward the positive terminal. Electrical forces across cell membranes affect functioning of all cells, and small electrical currents carried by ions are essential to muscle contractions and nerve function. Again, later in the lecture series, when we get into the muscular system, you will see how these types of aqueous solutions and its ability to allow the electrical currents to be carried throughout these tissue structures is important.